Well, good morning, everybody. Welcome. And today we're going to start in on not one of the 7 subsystems, but what I referred to as mission design, that Brown referred to as orbital mechanics. Thanks for the input on that. I really appreciate it. I hope you had a good time skimming the chapter. A little bit about Brown. Brown's background is in mission design, but more so in propulsion. So those two parts of the book tend to be a little bit larger in terms of volume and also more focused. As many of you found out in the mission design orbital mechanics overview, Brown starts out with basic definition of orbits, types of orbits, and then moves into, at the end of the chapter, interplanetary design, using a method that he was comfortable with called the method of patch conics. At the University of Colorado, particularly if you go on to study orbital dynamics in more detail, you'll look at other techniques to calculate transitions from one planet to the other that actually work out a little bit more quickly than does patch conic. But from my perspective, the patch conic approach shows you how to think about a spacecraft that leaves one planet, moves through space and gets to another. Today we're going to cover some general ideas and things that you need to know to support some of the analysis that's required for the overall program. So that's what we're going to talk about during the class period today. We typically spend 3 class periods on this, but because you're so special this year, we're only going to spend 2 and go through the same amount of material. As an aid to your learning, however, and I think I sent out an email notification on this over the weekend, that we've put up all the lectures from last year onto the website, so you should have access to that. There are 3 lectures in mission design that are up there. Some of what we'll cover today is in those lectures. Those lectures tend to cover a little bit more detail, less specific to design and some extra information. But please, if you would like, refer to those lectures, and those are accessible to you to help in this class going forward. Another thing I'd like to say is that we're in the process of creating teams. I know Amal has put some information out, trying to collect information. You're putting information up on D2L to give us some team idea. There's still a little bit of an open question for people who are taking this from a distance. And so I sent out an email this weekend describing some options for people who would like to take this class from a distance. And 3 choices, basically: to participate, as some of you are, in the class itself, even though you're signed up through the outside process, you're here, and that's good. Some people on the outside would like to join the team, and after class today, we'll discuss with Matt and I will discuss how we might join those, and there may be another team that gets formed outside of the class for distance students alone working together. So that's kind of where they are. If you would, though, if you're in class and you don't have a team, would you raise your hand? Good. Okay, we're getting a little more firm on that right now. So any questions before we begin? Okay. So this is the solar system. You're familiar with all the planets. All the planets here are, and we can quibble about whether Pluto's a planet or not. I don't know. Raise your hand. Is Pluto a planet? Raise your hand. Is Pluto not a planet? Raise your hand. Oh, good. Okay. Pluto is not a planet. Anyways, all the planets that you're looking at have an interesting characteristic. They're all moving into the plane of the board. They are from the, let's say, a top view from the north ecliptic plane view. They're all moving counterclockwise. Those are called direct orbits. The planets move in an orbit for a reason, and one of the reasons is they're trying to escape. They're trying their hardest to escape and get away. The problem is that the sun, because of its ability to gravitationally hold onto those planets, keeps those in orbits. And so this is what we're going to talk about a little bit today. Each of the planets has an interesting characteristic. They all rotate on an axis. None of the axes are aligned, so they're tipped with respect to the orbital plane that they're in. All of the planets rotate in what's called something related to the ecliptic plane. That's the plane that the Earth rotates in around the Sun. Each of the planets is inclined with respect to that orbital plane. Each of those planes tend to move with time, and we'll talk about those on Wednesday, but that gives you a general idea. It's very convenient that the planets all move in the same direction, otherwise they'd be really difficult to get to if they didn't. Let's talk about a couple of concepts that are important to understand, and that's a concept first of two bodies with mass being attracted to each other. So if we take two bodies, put them in space, each of them having a mass, they're attracted to each other according to the expression shown here, meaning we multiply the mass of the two bodies times the universal gravitational constant divided by their radius squared. So force, or the connecting force between them, is just a function of the mass of those two objects, the distance that separates them squared. So as things start to move apart, the gravitational attraction changes as the square of the distance. Betty knows a little bit about the other aspect of this, and this is called acceleration as a result of velocity. So what Betty's trying to do is she's trying to accelerate and put as much velocity on this mass as she swings it around, and the force that her hands and her arms have to offset is equal to mass times the velocity squared divided by the radius. So Betty's job to get as much force as possible is to take that fixed mass, put as much velocity as she can on it, and extend her hands as far as she can and still maintain control. If we take a look at the fact that we've got a fixed mass, let's say an Earth or another body with an orbiting satellite around it, we have two aspects taking place. We have that satellite moving at a velocity, essentially the mass at the end of Betty's wire, that's being held in place not by a wire but by the gravitational force of the planet that it's orbiting around. If we take essentially the speed of the satellite and the force that it creates and match it to the gravitational attraction provided by the body that the spacecraft is orbiting around, we can solve quite easily for the answer. And you'll notice right away that the mass, m1, which in this case is the mass of the spacecraft, drops out, and we're just left with an expression where velocity equals square root of gm divided by r. And Brown simplifies this expression here and relates it to a parameter he calls mu. So every planet has essentially a mass, and when we multiply it by the universal gravitational constant, we end up with a value of mu for each planet. So if you said, what's the velocity of a spacecraft in orbit about a planet at a particular radius, all we'd have to know is what planet was it, universal gravitational constant, planetary mass, the radius at which the spacecraft sits to find its velocity. Okay, a little bit about this parameter called mu in kilometers cubed per second squared. So if you look at various bodies, you've got the sun at the center of the solar system, the sun sitting at a very large number, and then the other planets next to it, Mercury, Venus, Earth, the Moon, and Mars. You start to get an impression that if you get anywhere near the sun, because of the sun's ability to gravitationally attract, that the sun is going to be the dominating force. And it turns out that in interplanetary travel, as we're around a small planet like Earth or Mars or Venus, that the gravitational attraction from that planet dominates its motion in the local area. But as soon as we get away from that planet, as soon as we start to move, the sun becomes the dominant factor in motion. So just to give you some idea that the sun, with its physical mass, is many orders of magnitude larger than any of the planets, and the sun becomes a dominant body in that area. So what happens? Well, if we put a small satellite out next to a planet at a particular altitude, In this case, let's call this H. And we don't do anything, what's going to happen to that small body? Well, it's gravitationally attracted to the Earth, and it's slowly going to get put into the Earth. If we give this a little bit of velocity, it's going to try and escape, but eventually will be pulled back into the Earth because of gravity. And what we're looking for is the condition where gravity always pulls this around, but not enough to get it back onto the Earth. And I think in Brown's book he refers to this as Newton's cannon, where we finally have a spacecraft in orbit that has enough velocity where it doesn't get pulled back to the Earth, nor does it leave the Earth environment as well. And so we know that the velocity expression for this is just the square root of mu over r. So for launching something off the surface of the Earth, what we would like is to have a launch vehicle essentially take us to this altitude, apply enough velocity so that this object is moving at the proper velocity when it leaves the launch vehicle and stays in Earth orbit. Okay. Some assumptions that Brown puts forward, some that are true, some that are going to have to be modified as we go on. One is that there's only two bodies, okay, the planet and the spacecraft. As you go on to further design and analysis, you'll start to include different aspects. The moon becomes important if you're in Earth orbit. If you're traveling to Mars, asteroids become important. For this part of the course, you don't need to know that, and that's fine. Brown makes a spherical assumption on both the planet and the spacecraft, saying that not only are planets and spacecraft spherical, but they also have uniform mass distribution, okay, uniform density. And that for purposes of discussion, we can neglect the mass of the spacecraft. Okay, so what happens? We put a spacecraft in orbit around a planet. That planet is spherical. The orbit is circular, meaning it's at constant radius. And when I say radius, what I mean is radius from center of the planet to the object, okay? In some problem statements in Brown, you're given a height above the planet. Keep in mind that the radius is always to the center of the planet. And in the case of the Earth, we've got to add 6378 kilometers to the altitude that the spacecraft is at to give us the overall radius to the center of the object. Okay? Something to keep in mind. As long as we keep or have enough velocity on the spacecraft that perfectly matches its radius and perfectly matches the spherical Earth, then we stay in a circular orbit. Okay? Very straightforward. So, expression for velocity in a circular orbit, quite simply, velocity is the square root of mu over r, where we've talked about parameters represented to each of the planets and the radius from the center of the planet out to the center of the spacecraft. So I came to you and said that there's a spacecraft in orbit at 1,000 kilometers above the surface of the Earth, and I wanted you to calculate the velocity. You would say, well, the velocity equals the square root of mu over r. Mu of the Earth is 398,600 kilometers cubed per second squared, divided by the radius, which is 6378 plus 1,000 kilometers. You'd solve for that. And you'd probably find out that the velocity is somewhere around 7 kilometers per second, which is sort of the velocity where most objects in Earth orbit are riding right now. Okay? Simple, straightforward. Any questions about that? So you now know how to calculate the velocity of a spacecraft in Earth orbit around a spherically symmetric Earth in a circular Earth orbit. Now I'm about to tell you that this is a particularly difficult thing to do. Let's move on and make another assumption. Let's say that there are two bodies, but that the spherical nature of the planet is now up for question. Okay? Planets aren't spherical. In fact, the Earth has an interesting property. Because the Earth spins on its axis, the Earth tends to be what we call an oblate spheroid, meaning it's fatter at the equator and compressed at the poles. So it looks kind of like a squished sphere as it sticks out. Okay? If the two-body assumption holds, orbiting body paths are conic sections where the focus must be at the center of the body. Well, this is interesting, that the only orbits that we can develop are sections of a cone, meaning a circle, which is shown in the middle and we've already talked about. If we add something to a circle, let's say we have a spacecraft in circular orbit, and at a particular point we apply a velocity change to that, we can actually put the spacecraft out on a different orbital path into an elliptical path. If we would do the same thing as the spacecraft came around and add a velocity change at this point, we could put the spacecraft on an outbound trajectory that takes forever to get to infinity. This is called a parabolic trajectory. Parabolic trajectories are interesting because they're the, if you will, the cutover point from a closed orbit, an elliptical orbit, to something that has some additional velocity put to it, and that's known as a hyperbolic orbit or a hyperbolic departure orbit. These orbits have properties called eccentricity, meaning it gives you an idea of how, essentially, how large the orbit is or what the parameters are. A circle, for example, has an eccentricity of 0. An ellipse has an eccentricity between 0 and 1, a parabola an eccentricity of 1, and a hyperbola an eccentricity greater than 1. It also has referred to it as different energy levels. So both the circle and ellipses have energies less than 0. We call these closed orbits. And as we move away from closed orbits and add more energy, they become open orbits. Hyperbolic trajectory, which we'll talk about in the next lecture, is perhaps the most useful of any of the orbits. It's the only orbit path that we can use to leave a planet. Essentially what we're doing is putting energy in to get away from the gravitational attraction of the planet and then adding a little bit more to get us outbound and going forward. So all orbits are conic sections, or let's say pathways, sections of cones, and we can do some things to maintain those. So let's talk about this circular orbit. You would think that, if we just put a spacecraft up into orbit around a planet, it's going to be really easy to obtain a circular orbit. Turns out that this is a circular orbit with an eccentricity of 0. It's very difficult to obtain. And the reason for that is that when you look at the properties of planets, not only are they not spherical, as I said, the Earth is an oblate spheroid, but mass is not uniformly distributed. Gravitational attraction around the Earth, in particular, varies as a result of where we are. So think of flying over the Earth with fixed gravity. That wouldn't put any additional force on your spacecraft. But now imagine an Earth where gravity changes at each location. You've now got your spacecraft speeding up and slowing down, speeding up and slowing down. And that does certain things to the overall orbit. So what I'd like to do is talk a little bit not about the circular orbit, but is what is likely more common is the elliptical orbit and some of the parameters of the ellipse. I'm just going to throw it out and say this is something you have to remember from this lecture, that velocity is the square root of 2 mu over r minus mu over a. I'll explain to you what those are. You already know what this is. It's the spacecraft velocity. You already know what mu is because we've talked about that for planets. You already know what r is, which is the radius from essentially a point in the orbit or the body we're orbiting about to the spacecraft. The only thing we need to define now is what is A and how does it relate to things. But it turns out that this equation, known as the vis-viva equation, can allow you to calculate velocity in any type of orbit in any type of orbit shape. So a real useful equation to remember. If you're a visual person and you want to remember this equation differently, okay, it's just the velocity is the square root of 2 times the yellow circle. There's 2 yellow circles in this equation, a blue box and a red box. You already know the yellow circles in the blue box. This is the only thing that's different, okay? Velocity is the square root of 2 mu over r minus mu over a. Okay. A little bit about definitions. We need a planet to rotate and orient ourselves about, and that planet is at the focus of the ellipse. Some parameters related to the ellipse. First is the distance from this focus to the nearest point to the focus area. That's called r sub p, radius of periapsis. So radius of periapsis is the distance from the center focus out to a point of closest approach to the planet. Okay, we call it periapsis. It's odd because I wanted it to be a different word, because the furthest point away is called apoapsis. And for me, it would have been much simpler if the A was associated with the closest point and the P was the furthest away, because I would think of A and P, A would be close, P would, no, it's just the opposite. So now I have to remember that P is closest and A is further away. So I don't know what mnemonic you're going to use, but that's the one I stuck with when I first started to learn about this. The line connecting the point furthest away and the point closest to the focus is called the line of apsides, or the line of apsides, depending on which camp you're in. I'm in the apsides camp. I don't know why. I just like 3 syllables. Apsides just seems too short for me. So line of apsides connects periapsis and apoapsis, and you'll notice it goes through the focus. Depending on where we are, there are different names for periapsis and apoapsis. The general term is periapsis and apoapsis, but for the sun, orbits around the sun, the closest point to the sun is perihelion. Makes sense, helion being a reference to the sun. Furthest away is apohelion. We could talk specifically about the Earth, perigee and apogee, and the moon, perilune and apollune, and in planetary coordinate systems, there'll be other names as well. So I stick with a generic name, periapsis and apoapsis. You can be an overachiever and actually pull out the correct names for the planets or moons that we're working around, okay? There's a line from the focus to the location of the spacecraft. That would be the radius that we're concerned about in the vis-viva equation. So if we're calculating parameters of the spacecraft, velocity of a spacecraft around an elliptical path, using the vis-viva equation, we would use mu of the, essentially the planet they were around. We'd use the radius from the center of the planet out to the center of the spacecraft. And then we would need another factor called A, which is the semi-major axis. And A is just half of the distance from periapsis to apoapsis. So if we know what apoapsis is in terms of radius, we know what periapsis radius is. If we add RA plus RP divided by 2, we get A, which is the semi-major axis. Okay? And from this, we can determine what the velocity is. Another parameter that's useful is shown here with this Greek symbol. This is called the true anomaly. So the true anomaly is the angle from the line of apsides out to the radius to where the spacecraft is located. So you can see that the true anomaly starts at 0 and goes out to 180 degrees and then comes back to periapsis. So you can imagine that if this were a less elliptical orbit, if things started to compress, if they did, then semi-major axis starts to look more like, and when it finally gets there, the radius of a circle. So if we take the vis-viva equation, square root of 2 mu over r minus mu over A, as essentially the semi-major axis goes to 0, it becomes non-existent, or A goes to R, excuse me. We've got square root of 2 mu over R minus mu over R. We're just left with the square root of mu over R, okay, as the velocity. So as ellipses get smaller, we take the vis-viva equation and it just comes back into the equation for a circle. Any questions about lines or references to the ellipse? Okay. True anomaly, we've talked about true anomaly being the angle from the line of apsides out to the radius vector out to the spacecraft. Eccentricity is just an expression that says how big is the circle, and eccentricity is essentially an expression that relates to C and A. That gives us an idea of what happens. We can also get it by knowing the radius of apoapse and the radius of periapse, subtracted, divided by 2. Last thing I want to talk to you about, because it's important, is what we call flight path angle. Okay, as the spacecraft is moving around the orbit plane, the velocity vector of the spacecraft has a relationship to the orbital plane itself. If the spacecraft is at periapsis, its velocity vector points in this direction. The velocity vector is tangent to the ellipse at this point in time. We say that the spacecraft has 0 flight path angle because the spacecraft velocity vector is tangent to the orbit plane. As the spacecraft moves through its orbit, we can start to generate and look at the radius vector, the normal to the radius vector, and the angle that gets created between essentially the normal to the radius vector to the spacecraft and the velocity vector of the spacecraft itself. Okay? Think of it as the spacecraft moving with relation to the body it's moving about, and that has a direction, but the velocity vector is pointed off that position. Follow the spacecraft through, and what you'll find is that the flight path angle essentially changes until it gets to apoapse, at which point, again, the velocity vector is tangent, meaning it's coincident with the direction of the spacecraft. These are key in terms of our ability to move from point to point, and if we can find points in the orbit where the velocity vector and the orbit itself are tangent and apply velocity change, we get essentially the best condition for moving, the most economical propulsive condition that we can have. And I'll talk a little bit more about that. Brown develops a number of relationships in the book where if you know a couple of things, C and A, for example, you can get eccentricity. You can also get in eccentricity by apoapsis radius in A minus 1. We can get eccentricity by looking at various relationships. So it turns out that in orbital mechanics and orbital design, if you happen to know one or two things, you can also figure out many other things. And Brown, I think, does a particularly good job inside the book to define what these relationships are. All right, some of the magic involved. If we're on a circular orbit, okay, and we add velocity at a particular point to that vehicle, we change the orbit of that vehicle. So if we're in a circular orbit to begin with and we add velocity right at this point, we change the orbit. And now we create an eccentric orbit that has a periapsis and apoapsis. Spacecraft returns and comes back to this absolute point. Pretty cool. If we're coming back and we're at this same point again, we turn the spacecraft around and apply the equal but opposite velocity, we put the spacecraft back on its original circular orbit. So moving and extending the orbit, add velocity, bringing the orbit back to where it needs to be, reorient the spacecraft, apply opposite velocity, slow the vehicle down, and now we're in different orbits. Wherever we apply velocity, we set the periapsis point. So if I didn't apply velocity here, if I applied velocity change here, I would still put the spacecraft on an elliptical path, but in this case, the new periapsis point would be at the location of the velocity change. Okay, velocity, circular to elliptical orbit. How would I do it? Start out with a circular orbit, and I apply a velocity change. What's the velocity that I've got at this location? How do I calculate it? Well, I can look at the vis-viva equation and say velocity is the square root of 2 mu over r minus mu over a, but I already know what that is because we just wrote it. It's just the square root of mu over r. Okay, so the velocity would be, let's say we're the Earth, 398, 600, divided by the radius, and let's say we're at 600 kilometers altitude around planets, so we'd be 6378 plus 600, square root of that. That would tell me the velocity on the circle. If I wanted to move this out onto a larger ellipse, I'd have to have an instantaneous velocity increase at this point in time that I can calculate by velocity to the square root of 2 mu over r minus mu over a. I would have to then say, okay, what are the orbital parameters, and in particular, what's the semi-major axis that I want to have? Go through, plug in velocity to the square root of 2 mu over r, which is the same r, minus mu over a, which is the new semi-major axis. And then I would come up with, let's say, velocity. I have velocity on the circle. I have now velocity on the ellipse, even though spacecraft are the same place. The velocity difference required is just the difference between these two values. So if I could fire a rocket, instantaneous rocket, and change the velocity at this point with this kind of velocity change, then I'm able to go out on an elliptical path. All right? So I take, in reverse, the velocity that I would require at the new periapsis point by the vis-viva expression and subtract the velocity that I did have on the circle to give me what we call the delta V required. Make sense? Okay. Flight path angle we've talked about. Flight path angle 0 at periapsis, 0 at apoapse. Flight path angle is positive with r increasing. Okay. We come to 0 flight path angle, and then we refer to it as negative on the return. So flight path angle positive going out, negative coming back in. One of the most important transfers that we can make using velocity change is what we call the Hohmann transfer. This was designed quite a while ago, and it's one of the most important transfers and maneuvers we can make. It relates strongly to interplanetary transfer, where we've got planets orbiting about a large gravitational body, the sun, and we want to move. But let's suppose that we wanted to go from one circular orbit to another circular orbit. So if we're on the initial circular orbit sitting here, going at a particular velocity, the square root of mu over r, and we want to move out to an orbit with a new radius, but also circular, we have to change velocity here, as we just talked about, to put us on a transfer ellipse. And then we have to change velocity out here as well to put us on a new circular ellipse. So we'd start out at point 1, knowing we're on velocity of point 1. It's just the square root of mu over r. To get on an ellipse that brought us out to this point in time, we'd have to calculate the semi-major axis of that ellipse, and we'd have to apply velocity at point 1. The new point 1 is square root of 2 mu over r minus mu over a, where a is the semi-major axis of what we call the transfer ellipse. Okay? If we take the delta of these, that would give us the velocity change required to be here. If we get out to the new radius but don't do anything, what happens? We just come back to the original point and stay in an elliptical orbit. So what we have to do out here is apply another velocity change, essentially increase our velocity. We know what the velocity is on the ellipse because essentially we've calculated here, and we just have to change r to get the velocity on the transfer ellipse, and then we have to calculate using the original expression with the new r what the velocity is on a circle, take the difference, and then we have delta 1, delta 2. Now we know by adding these together the sum of the velocity changes to get us out to a circular orbit. So if we want to change orbits and orbit diameters or modify the orbit that we're in, we apply velocity changes at particular points in time in a very, very simple way to change the orbit parameters and orbit properties. All right. So now we know that we can go from one orbit to another with velocity changes. We know where to apply those velocity changes. We know that the best way to do that is to apply those velocity changes tangent to our orbits. So if we're want to go from circular to circular orbits, we can apply velocity changes anywhere because they're always the flight path angle on a circle is always 0. If we want to go from an elliptical orbit to another elliptical orbit, we kind of can think about it and say, okay, if we go from one elliptical orbit to another, where's the best place to apply the velocity change? And that would be at either periapsis or apoapsis because we've got 0 flight path angle. Okay? We're tangent to our departure orbit. We're tangent to our arrival orbit. All right. Let's talk about taking our circular orbit. Let's add more velocity and more velocity and more velocity until finally there's not enough gravitational attraction to essentially bring us into a closed orbit. At this point, we break open the orbit, and the spacecraft leaves with just enough energy to get away from the body that we're orbiting around. Okay? So the semi-major axis becomes infinite. This term goes away, and we're left with velocity is just the square root of 2 mu over r. This is not a particularly useful orbit, but it's also known as the escape velocity for a planet. So to figure out how much velocity we need to leave a planet, right? We're trying to leave the planet and get away from it, that if we apply this kind of velocity change to it, we can reach what's called escape. Now, if we've got enough energy to escape, the thing is we're just getting away from the Earth's gravitational attraction. The spacecraft itself doesn't have much velocity, any velocity to go with it, so it sort of manages to keep going away from the Earth and goes somewhere, but not in a targeted sense. For us to actually make use of escape velocity, we're going to have to add a little bit more velocity to that escape to give it a direction and a pathway to move in. But if you wanted to know what's the difference between a closed orbit and how do we get out of a closed orbit into an open orbit, We can look at the vis-vivo equation, just drop out one term, and then we're left with just the square root of 2 mu over r. So if you want to know what's the escape velocity of the Earth, well, it's the square root of 2 mu over the Earth's radius, 6378 kilometers. Okay? Finally is the hyperbolic trajectory, which looks a little bit like a parabolic trajectory, but it's got something different. And it also changes the sense of a vis-vivo equation. If we take and add to a parabolic orbit some extra velocity, we now have a way to leave a closed gravitational system on an outbound departure trajectory with known velocity, and if we know what the velocity is, then we can start to look at how does the direction and velocity of that spacecraft impact where we're leaving and where we're going. The way a hyperbolic trajectory is described is quite different than a closed orbit. Recall that we've been talking about orbits that have semi-major axes internal to the orbit themselves. In a hyperbolic trajectory, we're talking about essentially a number that is outside of that orbit. Mathematically, it changes the context of the vis-vivo equation, where instead of the square root of 2 mu over r minus mu over a, now we have a negative semi-major axis. So it changes the negative under the radical sign to a positive. So the velocity at any point on a hyperbola is the square root of 2 mu over r minus a minus mu over a or plus a mu over a. Okay? So if we look at what we're talking about in terms of the context of what's underneath and impressed here, we can break this up into two pieces. We've got the square root of 2 mu over r, which is just the escape velocity for a particular planet, and then we've got another expression called mu over a. This is the velocity that the spacecraft leaves the closed gravitational system with on a journey to somewhere else. Okay? From an expression perspective, particularly at Earth, we call this the hyperbolic excess velocity, VHE. If we take VHE and put it under the radical sign, we've got to square it so that the units come out right. So this term is known as hyperbolic excess velocity squared, which in the business of launch vehicles comes back to something called C3. So if you go out and buy a launch vehicle, what you're buying from the launch vehicle provider, particularly for an interplanetary mission, is a parameter called C3, which is the hyperbolic excess velocity squared. That's what they're selling you. So a launch vehicle provider is getting you away from the Earth's gravity, and then they're allowing you to have extra energy, and it's that extra energy that gets you to a different place from if you're traveling from planet to planet. Okay? Closed orbits, circles, ellipses. Circles are difficult to obtain. Most orbits are somewhat elliptical. Even highly circular orbits have some eccentricity to them, just because orbiting planets that are not spherically symmetrical and have distributed gravity systems tend to muck with the gravitation or tend to muck with the velocity of the spacecraft. So velocity are always kind of speeding up, slowing down. That is just like providing propulsion. So it sort of changes the eccentricity and shape of the orbit. Okay. Circles, ellipses, parabolas, useless from a design perspective, but good from the understanding that I've got to get away from the gravitational attraction of a body. I'm going to apply this much velocity to get away from the planet. And then hyperbolic excess velocity. We add a little bit of velocity to the escape velocity, and that gets us from here to there. The launch vehicle can give us that, or we can create it with a rocket on the spacecraft. If you're buying the rocket suppliers like to talk in terms of a quantity called C3, which is hyperbolic excess velocity squared. And C3 will relate to the amount of mass that you want to put into orbit. So 4 forms of the vis-vivo equation. in its standard form, square root of 2 mu over r minus mu over a. A circle, straightforward, square root of mu over r. Ellipse, 2 mu over r minus mu over a. Parabola disappears because we've got an infinite semi-major axis. So we've got escape velocity. And finally, on hyperbolas, we've got a way to calculate velocity at any point. And because of the way we treat the semi-major axis, the form of the minus sign flips to plus, and we end up with an expression for the escape velocity and hyperbolic excess velocity squared, or C3. All right. So let's put it all together. Why is it important? Oh, wait a minute. Stand up for a second. Stand up. Anybody want to talk about anything? What do you think of the ban on people coming into the country? Disappointing. Disappointing.
I mean, angry about it, basically.
Angry? It happened really fast. Yeah. Appears not to be very well coordinated. Yeah. How many people are worried about what Trump is doing? Yeah. Yeah, it's a little concerning, isn't it? Yeah. Anything else you want to talk about? Did everybody raise your hand if you didn't have breakfast this morning? Did not have breakfast this morning? How can you come to class without having breakfast this morning? It's the most important meal of the day. Yeah. Okay, let's get that corrected, all right? All right. Have a seat. Hungry. Remember the picture I showed you, the planets? Got the sun, and it had all the planets lined up, to one spot onto the right. So let's talk about a little bit, jump ahead and talk about planetary transfer. If we're talking about all of the planets being in circular orbits, let's say Earth would be here, and Mars would be here. And we assume that these are circular orbits, how would we want to go from Earth to Mars if the Hohmann transfer was employed? What would be the best way to do that? Go ahead.
So, like, by the time when you initiate your velocity jump from the Earth's orbit, and you need to coordinate it such that the mass, the planetary mass is right there for it to enter into orbit so that it will.
Yeah, what would be convenient is for us to leave Earth and then have Mars arrive exactly 180 degrees away from the planet, right? And to have flight path angle on the Earth's circular orbit be exactly equal to 0 flight path angle on Mars orbit, and then we could leave Earth and arrive at Mars with the most optimum velocity changes, right? Velocity changes are optimal with 0 flight path angle, okay? So if the planets were all in circular orbits and we could schedule the planet Mars to be here at exactly half the period of this orbit and arrive there, then it would be the most optimal. Okay? Is Earth in a circular orbit? No. Is Mars in a circular orbit? They're both in elliptical orbits. What does that tell you about leaving Earth and leaving Mars? It tells you that you're on a different flight path angle, not 0, but something else when you leave the Earth. And it also tells you that you're probably arriving at different flight path angle, meaning your velocity vector and the planet are going in 2 different directions and you need to correct. Okay? Anything else that comes into play? What's the chances that Mars is 180 degrees away when this happens? Almost never happens. So Mars is either someplace over here or someplace over here, and so we have to adjust our trajectories to get there. Okay, that means either a longer or shorter trajectories and more difficulty intersecting the planets. And Mars is one of those planets that has an interesting period. Every year it's sort of next to us, and the next year it's away from us, next to us. So the launch window out to Mars, what we call a synodic period, is one of the most difficult to get to because it's in resonance with the Earth orbit. If we go further out to the outer planets, we can go almost every year because they tend to look like they're on the other side of the sun. To the inner planets, more time and thought has to go to it, but Mars is about the most difficult planet to get to. What we would like is for everything to line up like this so we'd have the ability to do a home and transfer. Another thing that's really a challenge too is that none of the planets are in the same plane. They're all tipped with respect to the Earth orbital plane. So if we're leaving the Earth to go to Mars, we either have to go up on a small angle or down on a small angle. Those small angles take a lot of velocity change. So getting to Mars or getting to any planet often becomes a very difficult challenge with the rocket capability that we have. But we would figure out how to go from one planet to the other in a straightforward way by just taking essentially the velocity, in this case, of the Earth, which is the square root of mu over r, with mu being the sun and r being the radius from the Earth to the center of the sun. That would give us the velocity of the Earth. We can forget about these two things. And then calculate the velocity needed to go on the ellipse, and we could find out, in general, how much velocity change we need to apply to get away from the Earth at its simplest form. So now you know how to calculate velocity change to go from Earth to another planet, assuming perfect conditions. And on Wednesday, we're going to talk about, well, maybe there's a little bit more to think about besides that. But for first order, yeah, sure, why not? That's what we can consider to do. Okay, we can define orbit and different orbit properties by looking at where the spacecraft is in orbit. And so here's a case where we can figure out properties of the orbit by, at one period of time off the planet, looking at where the spacecraft is and figuring out its true anomaly, and at a later time, looking at where the spacecraft is, and again, noting its true anomaly. So if we take R1, theta 1, R2, theta 2, and plug them in to the equation we have here, we can eventually come up with the eccentricity and radius of periapsis. Can you think of where this would be useful, where these two numbers would be useful? Let me tell you where they would be useful, is that if our spacecraft were in orbit and we had an antenna on the ground and we sent a radio signal out to the spacecraft, and the spacecraft grabbed that radio signal and sent it back to us, and we could calculate the time it took to get the radio signal out and back, we could then look at, because it's moving at the speed of light, we could look at how far away the spacecraft is. And if we read the antenna angle off the ground, we would have one of the data points we would need to determine where the spacecraft was. If we waited time t later and looked at and did the same thing, broadcast up to the spacecraft, looked at the return information that came back and calculated a second radius and a second distance, all of a sudden we're starting to figure out what the orbit properties look like. So this is in fact what we do. We look at launch a spacecraft in orbit. It doesn't really know where it is. The launch vehicle might give us the location and vector once things leave, but we have to start looking at the spacecraft and figuring out how far away is it, and using ground information what the angle it's at, so we can start to build its properties. And you can imagine that as more and more signals are provided, we become more knowledgeable about the location of the spacecraft, right? So ground antennas become important in terms of solving this. So again, very simple, very straightforward to be able to calculate the orbital eccentricity and the radius of periapsis, and that gives us essentially the definition of the orbit in 2 points. All right. You got your spacecraft in orbit, and you want to change the plane of the orbit. We launch out of Kennedy Space Center at 28.5 degrees inclination. The inclination of the orbit, if we go directly east out of Kennedy, is equal to the latitude of the launch site, 28.5 degrees. The minimum inclination we can achieve out of a launch site is numerically equal to the latitude of the launch site. If I launch at the equator, what's possible? Zero inclination, right? Equatorial orbit. If I launch out of Kennedy, the minimum inclination I can get is the latitude of Kennedy. If I launch out of Baikonur, Russia, the minimum inclination I can get is the latitude of Baikonur. So what do? Well, change inclination. Okay? So if I'm on an orbital plane that's, let's say, inclined to the equatorial plane, and I'd like to change that orbital plane to be different, and I have to swing it through an angle of alpha, I have to pay an enormous price. I have to pay the price of the velocity I'm traveling at times the sine of the angle divided by 2. Okay? So if I'm in a circular orbit, that's a problem. Let's suppose that, however, I'm in an elliptical orbit where I'm close to the Earth, at one point, periapsis farthest away from the Earth at another point, and I want to change orbital plane. Where should I do it? I should do it where the velocity is the smallest. Velocity in the smallest being periapsis or apoapsis. Apoapsis, right? When I come around the Earth at periapsis, I'm screaming. I'm going really fast. When I get out to apoapsis, I'm essentially slowing down. So if I'm going to play the plane change game, I want to make sure that my velocity is as low as it can be to swing it through this kind of angle. So orbital plane change is highly intensive propulsively. Pick the place where you want to do it. Okay. Now, let's have some fun. Let's talk about the non-spherical Earth. Okay? Earth is, we take the Earth, and essentially what we do is we whack off the top and the bottom, and we make it fat around the middle. Give it some extra weight right around here, okay? This kind of looks like a cartoon character in a way. Whatever. All right, so I've got an orbital plane rotating around, let's take Earth for example, all right? And as I'm rotating around the Earth, if my orbital plane starts to become inclined, let's say I don't want to launch in an equatorial plane, but I want to launch in an inclined plane, my spacecraft now starts to go over something that's not symmetric, but is asymmetric. And what happens? A couple of things happen. That bulge around the Earth starts to do something. When that bulge sees my spacecraft coming up over it, it wants to accelerate the spacecraft, and it wants to increase the spacecraft velocity. And what it does is it starts to take my orbital plane as I'm rotating, and it wants to rotate the orbital plane in the plane of the orbit. Okay? So if I have essentially my line of apsides in a fixed position around the Earth in the orbital plane, let's say the line of apsides goes directly up through the Earth, through the North Pole. As my spacecraft starts to orbit, that line of apsides rotates around the Earth in the direction of the orbit, just because that bulge around the Earth is starting to pull it and starting to want to throw the spacecraft around. So I have to be aware that if I put an orbital plane around a non-symmetric body, that orbital plane is going to rotate in the plane of the orbit as a result of its inclination around this bulge. Okay? Pretty easy to understand. So that effect is happening. Okay, we call that rotation of apsides. Just that line between periapsis and apoapsis is walking around the Earth in the plane of the orbit. All right. A second aspect, and you've all experienced this. You get on your bicycle. You start moving, start going fast. You take your hands off the bicycle handlebars. What happens?
You crash.
You do in the beginning, but after you get good, what happens?
It's stable.
Well, tell me about that. What's keeping you balanced? What do you have that's helping you?
Momentum.
You have that, but you also have something else. It's a property of your wheels spinning around a center point. Angular momentum, right? Your wheels are spinning. They have angular momentum. If they're spinning forward, I'm riding my bike forward, my wheels are spinning forward. I've got mass that's rotating at a certain velocity, and I've got this big angular momentum vector sticking out of my axle on the front and the back, right? Okay. Just like your wheel has angular momentum, a planet moving around the sun has huge angular momentum. Think of that, a big giant mass with a certain velocity, right-hand rule, big angular momentum sticking out of the sun. There's no way we're going to push the Earth down, and it's just fixed, and its angular momentum vector keeps them there. Okay? Same way with an orbiting spacecraft. There's an angular momentum, picture it, vector as a result of your spacecraft orbiting the Earth. Okay? That angular momentum keeps that orbit plane fixed in inertial space. If there was nothing acting on it, the Earth would move around the sun. Your angular plane would just not move because it's got a big angular momentum vector sticking out of it. Here's the issue with the Earth. The bulge around the Earth wants to play havoc with that angular momentum vector. The fat part of the Earth wants to torque your angular momentum vector, okay? It wants to pull it. When the spacecraft is below it, it wants to pull that orbital plane up. When the spacecraft is above it, it wants to pull it down. So you've got this orbital momentum vector that's getting pulled around. Okay, funny thing about angular momentum, not funny, but fortunately an understandable thing, that if I take a spinning wheel versus a wheel that's not moving, well, let's do that thought experiment. I have a wheel that's in space, and I put a torque on that wheel. What happens? It just moves, right? If I spin up that wheel, has an angular momentum, and I put a torque on it, the wheel doesn't move in the direction I'm torquing. The wheel actually moves at me because I'm taking an angular momentum vector, torquing it, putting a little angular momentum onto the existing vector, which rotates the vector. A second effect we get out of the bulge in a planet is that because I've got an angular momentum system sitting around a planet that's asymmetrical, that's trying to torque my orbital plane. Those little bits of torque, every time the spacecraft goes over the Earth, those little bits of torque get added to the primary angular momentum vector and essentially process or pull that angular momentum vector around the Earth, the body that it's over. So the crossing point of the orbit from, if it's going from south to north, which crosses at a particular latitude, changes every time it comes up. It starts to move because that whole orbital plane is being pulled around. So now I've got a second effect called nodal regression as a result of the orbit I'm in, the planet I'm around, and the way that it moves. When you take both together, I've got the orbital plane rotating in its plane, right, because the non-spherical, non-symmetrical aspect of the Earth is causing it to rotate in its orbital plane. And I got the fact that it's got angular momentum and it's being pulled around on top of it. So I've got those two effects. So rotation of apsides, regression of nodes. Okay. try and look at a video. We'll see if we can. Any choices? What do you like?
That one.
Let's see if we... I know what you're saying. I know. No, I don't want to add on anything. Okay, this is from MIT. This is a demo of a bicycle wheel. Watch what happens. He's going to spin this bicycle wheel up. This bicycle wheel is going to essentially carry angular momentum, and he's going to do a magic trick. It's magic. Okay. Everybody got it? What's he doing and what is happening? Somebody, please explain this to me. I'm so confused. It's hanging there. And if I went and touched it, if I just put my finger on the wheel and went like this, what would happen? It would bump, right? Okay. So in space, it's not fixed. This very smart man, has to be because he's at MIT, this very smart man comes up and starts spinning the wheel. What's he doing to it? Putting energy into it. And what's the property that gets created?
Momentum.
Angular momentum, right? And he can leave it horizontal. Why? Why?
Because the angular momentum essentially resists the gravity.
It's got energy. It's in a state. It has angular momentum. And it's trying to resist gravity because gravity is trying to torque it, right?
Yeah.
Okay. So let's look at what gravity's doing when he lets it go. What's gravity doing? Trying to
Bring it back to...
Trying to torque it, right? It's creating a net torque. Angular momentum vector is sticking out that way. What's the gravitational torque doing?
Pulling it down, like at that angle.
No, it's creating a moment. Right-hand rule,
Yeah.
it's putting a little delta H sticking out of the board, right?
Well,
Hanging off, I've got an angular momentum system, right?
yeah.
It's just angular momentum here. But because the mass is located off the string, there's a torque being created.
Yep.
This angular momentum vector is trying to resist that torque. So there's a little delta angular momentum that's starting to want to, right? So as it goes around, gravity is just not letting it go. And it's just going, I'm going to make you go around, right? Why is it, well, what's this? Why is it, what's happening here? Friction, yeah, go ahead. Friction is doing what?
Friction's causing it to lose angular momentum over time. And
Yeah.
so it doesn't have as much ability to resist gravity.
Yeah, who's going to win out in the end?
Gravity.
Gravity, yeah. Watch what's happening and watch what happens at the very, very end. You're seeing a slow precession, and then, do you see that see the wiggle at the end? Okay, that's another property of angular momentum and rotational motion, okay? Everybody understand? Angular momentum. We have the same thing with, a spacecraft, where Spacecraft's got angular momentum, big angular momentum vector sticking out of the spacecraft. Let me draw it. So we've got a planet, a spacecraft orbiting. We've got a big angular momentum vector sticking out just from the orbital plane. Okay? The bulge in the Earth starts to torque that angular momentum vector. And when it does, it wants to take and add a little piece of angular momentum every time that happens. And so what happens is that we see the angular momentum vector actually swing out and create a cone. So it looks like the whole orbital plane is just coning around the Earth as a result of that. Okay? Pretty interesting, huh? A couple of things you should know is that if you look at apsidal rotation is maximized at various points depending on altitude and depending on orbital inclination. And you look and you'll see that essentially apsidal rotation is limited. That's cool how that happened. Basically comes to zero at a particular angle. Okay, so we can, if we place our inclination at a particular point, we can neutralize apsidal rotation. We can calculate how we rotate, and the expression essentially is fairly simple. Okay, property of the orbit, A and E. We've got the inclination, we've got the radius. We have a factor called J2. J2 sort of describes the non-spherical nature of the planet that we're moving around, and N is just the mean motion of the spacecraft as it travels around the orbit. Okay, what's interesting is that the inclination is what we call a critical inclination at 63.4 degrees, and it just happens to match the longitude of the Russian launch site. It's called the Molniya orbit, that you essentially put the spacecraft up into orbit with an orbital period, essentially periaps and apoaps stay fixed, the spacecraft rotates underneath, and if you build the orbital period long enough, like 12 hours, and you put a number of spacecraft up, you essentially get continuous or near continuous contact to the Earth. Or if you wanted to put an imaging satellite above the Earth and keep it there and watch what happened in the United States, you'd launch a large telescope, have it look, and it would always be up above the Earth at a particular period of time with the Earth rotating under it. So here's a case where you can take advantage of the orbital inclination and make it work. So rotation of apsides in the orbital plane, it's fixed at this fixed inclination. Everything appears to stay fixed. Nodal regression we calculate with a somewhat similar computation, again looking at the J2 effect, the bulge around the Earth, and the fact that we've got angular momentum. It's neat because we can essentially march the orbit in a particular way around the body underneath it by choosing the right inclination. And it turns out that if we slightly incline an Earth orbit beyond 90 degrees, not up over the pole, but just beyond it, we can make that orbital plane move about a degree per day. So as the Earth moves around the Sun, the orbital plane moves around the Earth at about a degree per day. And it appears to stay fixed with respect to the Sun. This we call a sun-synchronous orbit, which is quite useful for observing the Sun, for observing things on the surface of the Earth. So, in summary, today we've talked about different types of orbits, what they look like, how to calculate velocity change. We've related that to interplanetary design through the Hohmann transfer. We've talked about two things that happen around planets with the orbits themselves. One is orbital plane motion in the plane of the orbital plane. The other is essentially taking that orbital plane and walking it around as a result of moving the angular momentum vector. Any questions for today? Okay, we're finished on time. Thanks very much. If you're continuing to read, please read. You might want to watch the videos that are out there, too, to look at what's going on. Thank you.
So wow. Try to an email.